this video we will be seeing how to create this tubular joint. For any analysis we require 6 essential things. Those are how to create the part, the property to assign, and the assemblage of this property parts with the boundary conditions. Then comes the mesh. Finally, the type of analysis we are going to do. So we will see initially by step. First, go to the parts. In that part you can create the required simpler parts first. So here we have created those parts initially. I'll go to one of these things, brace. So in this, how to create this brace or edit this brace, under this option you can have this solid. Under the solid extrude we will have this section sketch, so where you can edit it for the required diameter, outside and inside diameters. Then see here there are options for changing the diameters for the dimensions which I have given. Instead of 10.5 I can give 11. So without any further delay we will go for the properties. And most important thing is we need to be precise in choosing the properties. Under this create option we will be having this set of variations for 3D, 2D planar, axis symmetric. Axis symmetric is used for bolts or some repeat where the axis symmetry plays major role. And this deformable or discrete object, analytical rigid, we are not going into it. We are just using this deformable for this solid steel structures. Then the type of structures, instead of solid you can opt for shell for analyzing tubular joints, where the thickness will be analyzed based on the shell. So there is the variations within the thickness cannot be analyzed, but exact approximate solutions can be obtained from shell elements. Then we can move further to property. Here for each and everything we need to first define the property part. For each and every part we need to define the property. Here the major properties concerned for steel structures are elastic and plastic properties. Under elastic we will be assigning the Young's modulus and Poisson's ratio. In the plastic, for the plastic we will be assigning the stress strain curve. But the point to be noted is this is based on the yield stress and plastic strain, not the just stress and strain. So the strain which we obtain needs to be converted to plastic strain, and this needs to be given as an input. This is one such example for Fe 240 steel. And once you define this property, further we need to go for assigning it as a, you need to save it as a section manager, solid homogeneous. Then we need to assign this one. Further moving, assembly. Once we have created these parts, this brace and cord separately, this separate tubulars, we need to assign as a single entity like T member or a Y member, X member, K member. It will be in the instances where we'll be having separate cord. For example, I'm showing just an example, and a brace, I have resumed it. See here these members have been separately listed out. Now what we need to do is we need to attach these two members into a single entity. For that we need to translate this instance, translate this brace. The translating is the major, is one of the important things, needs to be done carefully, because the point which needs to be chosen of curved surface needs to be precisely known earlier. Mostly the center point of the brace with the center point of cord will let us have a perfect match. See the center point, will have a center match. So that we need to give extra distance of brace, that is the d by 2 chord diameter d by 2 to this one. Once it is been positioned, we can merge these parts. Here it will ask for remove or retain or of the mesh geometry. We need to have all these things removed. So these two members are selected. Now it will ask me a new member is being generated. This is part 1. Now the additional part of brace will be below, which needs to be cut using solid extrude. It can be chosen with the existing shapes as that of sketching the shapes in the part, so which will completely remove throughout the chord. So now we have a perfectly matched brace chord joint. Other way to do is, once you create chord, we can have that solid extrude at the axis chosen, like it will be like YZ axis chosen, so we can extrude the brace from that instead of cutting these things. Next, the step is the type of analysis we are going to do. For generally static analysis, we will be choosing static general when the analysis is up to the elastic limit. But after, for plastic analysis, we need to use static rigs because it will be having the post peak response where it will be unstable response is also possible. So it uses arc length method, for which the negative response is also taken care of, and the results are more precise than static general. And the outputs also, the outputs which we need needs to be defined here. The field outputs like stress, strain, which things we need, like forces, reactions, everything needs to be defined earlier, and the number of increments the each output should be, like whether it should be in the first output or second output, that frequency, like for 2 steps 1 output or 10 steps 1 output, based on the number of steps you are going to define. See, the one more thing is, here we need to define the incrementation. This is the point where the analysis can be started with, where we need to give the initial, if you are defining 0.1, it means 1% of the total load you have given or the displacement you have given. The maximum shall be the 1. So instead of giving 10 power 36 or 10 power 3, it's, if you define maximum as 1, it will be well and good, while the minimum, it will be fair enough to give 10 power minus 7, but I have given the worst cases 10 power minus 15 for the ground cases, for other cases where the contact is being there. And the maximum number of increments after the trial and error method I have chosen as 50. So the number of increments you give, the more will be the size of the ODB, so it will be taking time consuming as well as space consuming, and to take the output it will be very tedious. So after trial and error, approximately we can define the number of increments. Try to avoid giving higher increments. Interaction. Here comes the crucial part, where we need to give how this object will interact with each other. If there is a contact, the contact, everything needs to be contact or crack, it needs to be defined here. Else we can go with the rigid body assumption. For applying load, we need to have the brace member tied up to a single point for axial load cases. Else, if it is an axial displacement, there is no need of the constraints here, tie constraints, and these constraints is very helpful to create the sets where if you are giving stiffness or any other thing, the output is required. These constraints will help you to take the output from these constraints earlier, rather than going and selecting the specific surfaces at the later stage of post processing. It is better to define those constraints or sets here. For this constraint, for this brace, I have selected the rigid body and selected the top nodes of the brace and tied with a reference point. This reference point acts as the output point. Then at the later stage, the mesh size for solid elements, it is better to use solid brick elements of 8 nodes for approximate analysis. To have a much more critical analysis, it's better to use 20 noded elements. While the 8 noded elements will be most suitable for these bending problems and everything, and the stresses will be more approximate. Hourglassing effects are there. To avoid that, we will go for C3D8R, that is the reduced integration. And one more important thing is that how to optimize your mesh. Instead of giving a whole lot of finer mesh, you can just choose a coarser mesh of uniform mesh size under this global size. Here this error is due to, since the selected part is under assembly, we need to go for separate parts so that we can do this mesh size. One more important thing is, if the object is highlighted in green or yellow, if it is green it can be meshed with structured mesh, while if it is yellow it will be like a sweep mesh. It has two varieties of medial axis or the other things, but it is better if it is brown, it cannot be meshed with these regular mesh types. It needs to be like bottom up mesh or upper mesh. To avoid that, we need to partition each and every part. So here plays the crucial part of partitioning. Here I have selected, here I need to select the cells which needs to be partitioned. I have selected the cells or the faces or edges. I don't want this method. There are plenty of methods. It's based on datum plane, it's based on 3 points, or this is based on the extent phase. So here I need to select the cells for partition. I have selected the cells. Then I will select the face for partitioning. If I select this face, it will be partitioned completely. So we have the regular mesh categories like structure mesh and sweep mesh category. Here, to choose which method we want, we can select the whole or each separate part separately. If I give sweep and advancing print, everything will come under one category, and the size of the global mesh is defined here, where I can define the general rule is to use a width by 13, that is lateral dimension by 13 time divided by 13, or we can go by other way of selecting minimum at least 2 elements to 3 elements in the thickness direction, which will be more appropriate. And a finer mesh near the T joint would be more. Since I have given 2, a finer mesh has been created, and here 2 layers of elements are created. And then coming to load, we need to define the boundary conditions, and the load is defined here. Here there are plenty of things to be noted. First is, the boundary condition needs to be assigned as a pinned or axisymmetric of the corresponding to x or y z direction, or the fixed support. These options are given here in the symmetric or asymmetric boundary conditions. The other thing is, under displacement and rotation also, there is other set of boundary conditions to arrest this translation and rotation in the respective direction. So either way, both are same boundary conditions, but here we have the flexibility to choose which axis separately. So I have defined this boundary condition for this brace in the reference point. It should not sway in the x or z direction, and y it can move only in y direction, the two translation. Here I have given a fixed support at the chord ends. So since I am not using the constraints, tie constraints of rigid body, the encaster is throughout the chord circumference, whereas since I have used the constraint for this brace, it is specific to the reference point and it is not spread throughout the circumference of brace. And the load here I have defined using a separate concentrated force at the reference point. If you are defining load, we need a reference point. It needs to be connected to the nodes. And again, one more thing to be noted is x, y, z direction is usually represented in abacus as 1, 2, 3. So correspondingly we can define the load or moment. If it is 1 and 3, it will be moment, the force into the distance, while the direction 2 will be the axial direction in brace. See, comparatively the thickness, since we have chosen a minimum size, it is more finer mesh, but it will be computationally expensive, so go for a coarser mesh. And finally the thing needs to be done is job. Here we have plenty how the job needs to be executed. This restart options is generally available for static general if the analysis stops in between like 50 or 25 steps, else this option is not available for static rigs. And one more thing is this option, this job should be completed fully. Here in general nothing needs to be changed, whereas memory is the percentage of memory you can allocate for this job. It usually takes 90%, but you can restrict it to 70 or 60. But the disadvantage is if the job requires more memory than this, then the job will not be running and will be terminated. To avoid it, give this allow option. And parallelization, when the mesh size is higher and the step time is also higher, finer mesh is used, generally opt for parallelization. And this parallelization should be less than the course you have. For example, if you are having 6 cores, go for up to maximum 4 cores. And GPU acceleration is not that much efficiency. And finally, if you give right input, it will only have the input file. Data check is to avoid the errors which we have given initially, but these two commands are combined in submit option, where we will have the results also. And while the jobs are running, we have this monitor where you can see the incrementation taking place for each steps. And since it's a compression, up to certain point it was increasing in positive manner, and after which there is a negative which shows the ultimate stage has been reached. With this I conclude my video.